All right. Hello, everybody. All right. We've gone over the terrestrial planets. We've gone over the Jovian planets. Now we're going to look at the various kinds of minor bodies of the solar system. And that doesn't seem as big and momentous as talking about planets on the face of it, right? Planets are planets, they're worlds, and these are just small stuff, right? Well, you might think that. But the thing to remember about small things in our solar system is that the smaller something is, the more of them there are, right? One of the huge pieces of evidence for the nebular theory is that the most numerous, the most populous objects in the solar system are the smallest stuff. Why? Because all the big things formed from small things. That accretion meant that originally our solar system was nothing but small bodies, and that those small bodies accreted together and merged and crashed into each other and formed a smaller and smaller number of bigger and bigger things. And so when we're talking about the small bodies of the solar system, what we're talking about are the leftover planetesimals, the leftover building materials that never did accrete to form a planet or a moon or the sun. What we're talking about when we're talking about the small bodies of the solar system are we're talking about artifacts. We're talking about the time capsules that are left over from 4.5 billion years ago. These are the kinds of objects that all of the planets formed out of, and so all of the mysteries, well, maybe not all the mysteries, I may be overselling it, but a lot of the mysteries for how did we get to be here? How did our solar system form? Why is the Earth the way that it is? Why are we here? A lot of the answers are frozen in rock and ice in these small bodies. And so by studying them, we are studying our ancestors. We are studying the artifacts from the formation of the solar system. And so these objects are older and generally colder and much more fascinating than they might look like if you just look at a picture of this rock here or something. So when we talk about small bodies, here's a little sense of how small are we talking about. So here's the Earth's moon by comparison, right? And remember that our moon is one of the bigger ones. The asteroids are, well, the biggest asteroids are this size. The biggest asteroid in the solar system is Ceres, and then here's the sizes, or here's sort of the relative sizes of Ceres, Vesta, Pallas, and Hygeia, and those are just the 4 largest. Most of the asteroids in the solar system are much smaller than those, even. Your typical comet, so there's the size of the comet Hale-Bopp. That's the typical size of a comet. The comets tend to be all about that size, quite small. And then Eris, Pluto, Quaoar, Charon, these are some of the bigger Kuiper Belt objects. So if you notice, right, that the smaller something is, the more of them there are. In our solar system, we've got 8 planets, a couple of hundred moons. There's about 1,000 of these Kuiper Belt objects. So the KBOs may be small, but there's a heck of a lot more of them than there are planets or even moons in our solar system. There are hundreds of thousands of asteroids, and there's billions and billions and billions of these tiny little comets orbiting around the sun. So there's a lot of things to study when you're specializing in studying the small bodies of the solar system. There sure are a lot of targets to study, and some of them have some very interesting stories to tell. So let's look at a few of those. We clearly aren't going to get through all of them in one semester, or even in one lecture. But let's zoom in and look at these things in general. We kind of already talked about the Kuiper Belt objects before, because Triton probably was one. Triton, remember, is the largest moon of Neptune, and Triton is a bit strange as moons go. One of the big pieces of evidence that Triton wasn't always a moon of Neptune is that Triton is orbiting backwards. You know, remember, almost everything in our solar system is orbiting counterclockwise, but Triton is orbiting clockwise. And when you see a big exception like that, when you see an oddball like that in our solar system, that's a good guess. It's a good bet that it didn't form that way, right? It would be really weird if almost everything in the solar system formed going counterclockwise and Triton just decided, nah, I'll go clockwise. Nah, that's not how this works. That something happened to Triton. And the answer is probably that Triton is a captured Kuiper Belt object. I'll come back to this in a second. Remember from talking about the overview of the solar system that the Kuiper Belt is this big belt of billions of comets and also about 1,000 of these Pluto-type Kuiper Belt objects orbiting out beyond the orbit of Neptune. So if there was a planet that was going to capture a KBO and turn it into a moon, it would be Neptune, because Neptune's orbit is right inside the Kuiper Belt. And so probably Triton might be the first Kuiper Belt object that we have good images of. We may not have known it at the time, but it probably is. Pluto and the Kuiper Belt in general were discovered in 1930 up at Lowell Observatory in Flagstaff, and so for the better part of the 20th century, Pluto was the only Kuiper Belt object that we knew about. So we didn't even know there was a category of objects called Kuiper Belt objects. We just thought Pluto was sort of off on its own. It was the only one that we knew about. And then finally in the 1990s, we started finding more of them. It was the 1990s. We had modern telescopes. We had modern CCD cameras. With bigger telescopes and better cameras, you can see these small objects, and they are really small, right? These things are smaller than the moon, and they're orbiting way out there in the Kuiper Belt. The Kuiper Belt is between 30 and 50 AU from the sun. So 30 to 50 AU is a long way from Earth, and to see these small bodies at this great a distance, they look like tiny little specks in your camera. So they're very hard to study from a distance. This is an artist's conception of what a few of the largest KBO, Kuiper Belt object, that we discovered. They don't look like much, do they? And the answer is because, these paintings are sort of based on the best images that we had and the best data that we had of these bodies, of these KBOs at the time. Is this actually what they look like? Probably not, right? Surely there's a lot more detail. Surely they're not this smooth, this fuzzy looking. Like, surely there's a lot of detail to be seen on these objects. It's just that for most of these objects, the only images that we have are from Earth, and so they look smooth and they look like they don't have a lot of detail because we don't have a lot of detail in our images. In fact, this is the best picture of Pluto that we have from Earth. This set of photos, this sort of as Pluto rotated, they took several pictures so that you could map the whole surface of Pluto. These are the best pictures of Pluto that we have using the Hubble Space Telescope. And the Hubble Space Telescope is in low Earth orbit, so it's basically the same distance from Pluto as you are. It doesn't look like much, does it? Right? This small, blurry speck is not going to reveal its mysteries with pictures like this, right? And that's why we sent a mission to go there. The New Horizons mission was a probe that NASA launched to fly by Pluto, get up close, study it up close, so that you can get the kind of detail about what does Pluto look like, how does it work, what are its features, what are KBOs like, right? Because every picture we have of them looks like this, basically. And so if we know, and we don't know that much about KBOs from pictures like this, you gotta go up there. You gotta go there and study. And so that's what they did. NASA launched New Horizons in 2006. It flew by Jupiter to get grabbed by Jupiter's gravity and use Jupiter's gravity to give it a bit of a boost to pick up some speed the next year in 2007, and then it was just coasting. It finally got to Pluto in 2015. It was flying for 9 years. They got that thing going as fast as they could, and it still took 9 years to get to Pluto. Was it worth it? Let's see. Well, because what does Pluto look like when you get up close? The problem is, here's a picture of all sides of Pluto from the pictures that were taken. These pictures here don't look that good because they were taken from far away. These pictures here look a lot better because they were taken close up and you can get higher resolution, more detailed images. The problem with New Horizons is that they got it going so fast, it couldn't slow down. It just flew by Pluto, took as many photos and took as many measurements as it could when it was close up, and then it just kept on going. And New Horizons is still going, heading off in this direction, coasting on its own inertia, right? An object in motion tends to stay in motion, and they got that thing moving as fast as they could, and right now, it's gonna keep on coasting. So they only were able to get really good images of Pluto from one side, from the side that was facing the probe when it was at its point of closest approach. Right? So here's what Pluto looks like from close up. This, by the way, back here, this is Charon. This is the largest moon of Pluto. What do you notice? Is it rough or is it smooth? Bit of both, right? So is it young or is it old? Bit of both. Here, by the way, here's a black and white image of Charon. Why the black and white? So you can see the detail better. The full color doesn't give you as much of a sense of nuance of all the light and dark areas. So Charon is kind of what we were expecting. When New Horizons finally got to Pluto to see what it was like up close, we sort of expected it to look like this. Heavily cratered, rough, generally old, the thing you expect from small bodies, right? Remember, small bodies cool off faster. They cool off in less time. They go geologically dead in less time. And so an object that's smaller than the moon should have cooled off a long time ago, and therefore it should be rough, old, heavily cratered, and that's basically what you see here on Charon. If we look at a full map, the purple area there is the backside that we don't have good pictures of. If you look at the full map of Pluto and they put a little dot where every crater is. We can zoom in there. Those areas on the left side, the northern latitudes, the mid-latitudes, the Cthulhu Planum, those are kind of what we expected too, right? Lots of craters, heavily cratered, rough, old, been hit by a lot of impacts. The thing that surprised everybody, and I mean everybody, the thing that nobody was expecting was these areas over here that are a lot smoother. This East Tombaugh region has a lot fewer craters. This Sputnik Planum over here has not a single crater. It is very smooth. And that means, if it's smooth, that means it's really young. How old are we talking about? Well, those areas on the left side of the image, right, the mid-latitude, the northern latitude, the Cthulhu Planum, those are so heavily cratered that they're so rough that they would date back to about 4 billion years old. The East Tombaugh region has some craters, and that would put it at about 1 billion years old. So something happened to Pluto about 1 billion years ago. Something big, some big impact hit Pluto 1 billion years ago that laid a whole new surface over here, destroyed all the old craters, and in the last 1 billion years it's been hit a few times, creating a few craters. That Sputnik Planum, though, not a single crater. It is, geologically speaking, brand new. Now, geologically speaking, brand new means it's a few million years old. That area is probably a few million years old. Not old enough to have been hit by a crater in all that time. Nobody was expecting that. People were expecting Pluto to be like a lot of the small bodies, like the small moons, like our moon, like Mercury, right? Rough, old, heavily cratered, geologically dead. To find this area that has no craters was frankly shocking. It sure looks like Pluto has a bit of a heat source. That there's something that has kept Pluto hot and geologically active for a longer time. What could that be? Well, part of it has got to be tidal heating from Charon. That because Pluto is orbiting around that big moon, I mean, Charon is almost as big as Pluto is, that Pluto and Charon orbiting around each other gives each other tidal heating, and that, well, for one, gives you enough internal heat to power some volcanoes. But the surface of Pluto is ice. So these volcanoes didn't erupt with lava. They erupted with ice and water and slush. The term for these are cryovolcanoes. Cryovolcanoes meaning ice volcanoes. That when the heat inside Pluto, the heat that was generated from tidal heating, when it warmed up that water, the water must have melted, warmed up, and eventually erupted out of these volcanoes volcanically. Does that make it more of a geyser? Yeah, it kind of makes it more of a geyser. It's something like between a volcano and a geyser. I said before that New Horizons flew right on by Pluto. And after New Horizons flew by Pluto, they turned it around to take pictures of the backside, to take pictures of the nighttime side. And one thing you notice is all that haze. Pluto has an atmosphere. Little Pluto where the gravity is insanely weak. Remember what it takes to hold on to an atmosphere, right? In order for any body to have an atmosphere, you need to have enough gravity to hold on to the gas, and the gas can't be too warm. Well, the gas on Pluto is definitely not too warm. When you're out at the orbit of Pluto, the temperature is 40 Kelvin. The temperature of Pluto is 40 degrees above absolute zero. That gas is stuck there as an atmosphere around Pluto because it's not warm enough. Those molecules are moving so slowly, they're trapped by even the weak gravity of Pluto. And when you've got atmosphere, you're going to get some of the geologic features that you see when you have an atmosphere, like wind erosion. Pluto rotates about once every 6 hours, which means that atmosphere, and that atmosphere is pretty thin, but the atmosphere, although it's thin, is constantly blowing. That thin little atmosphere is constantly blowing across the surface, and the wind has carved this ice into these like jagged icicle scales. Let's look again at the Sputnik Planum, that smooth area on Pluto. Turns out, one of the things you might have noticed from that color picture, there it is, right, is that the Sputnik Planum, the left side here, is also kind of yellowish. What is that yellow stuff? It's ice, but it turns out it's nitrogen ice. That this smooth area is smooth because it's young, but also because of what it's made of. It's made of nitrogen ice. And, nitrogen, as in, most of the air you're breathing is nitrogen. Well, when you take the air you're breathing and cool it down to 40 Kelvin, it turns into ice. But nitrogen ice is not entirely solid. It's not exactly a liquid, but it's extremely viscous. It is extremely thick. And so the other reason why this area is so smooth is that it is not entirely solid. It's like a viscous, thick, very cold liquid. And so whenever an impact would hit this area, and I'm sure it has, whenever an impactor would hit this area, it would create a crater, and then slowly but steadily over maybe a few million years, that nitrogen ice would creep back into the crater and fill it in again. So if this area is kind of a lake, in a sense, a lake of super viscous, thick nitrogen ice. These mountains over here are made of water ice. So the mountains are made of water, and the plain is made of nitrogen. And if you look at this blows my mind. That little hill there, well, it's probably not little, it's probably a little big, but that hill right there is a chunk of water ice that is broken off from the coast, and it is floating out into the lake of nitrogen ice. And I say float because it's less dense. Water ice is less dense than nitrogen ice. And so that hill there is kind of like an iceberg that has broken off from the coast, and it's now floating into the lake very, very, very slowly. And in fact, if you look here, these ripples that we're seeing there are the wake. They're the wake of that iceberg floating into the lake. That's why that area is so smooth and so young, because it's kind of a liquid. And any cratering that happens eventually gets smoothed over. I said a minute ago that Pluto has that big moon, Charon. It also has 4 smaller moons. Pluto has 5 moons. Right? Styx, Nix, Kerberos, and Hydra are their names. If you look at the relative sizes, those smaller moons, Styx, Nix, Kerberos, and Hydra, they're about the typical size of a comet. And no coincidence, Pluto is orbiting out there in the Kuiper Belt with billions of comets. I wouldn't be the least bit surprised. Now, nobody knows this for sure, but I think it would be a safe assumption to make that those moons are probably captured comets. That they used to be comets, and then they got captured by Pluto's gravity, and they fell into an orbit around Pluto, and now they're stuck. When you look at these, especially Kerberos and Hydra, they're lumpy, they're irregular, they look like they used to be 2 comets that crashed into each other, and now they've smushed together to make one comet, or one moon or comet, I guess, depending on when you're talking about them. Which is, of course, what you'd expect, right? Everything is a merged body. Everything in our solar system was smaller things that crashed into each other. It's just that Kerberos and Hydra crashed into each other, and they're just smushed together and stuck that way, since whenever that happened. This is a completely different Kuiper Belt object. New Horizons flew by Pluto in 2015. By 2017, they had just finished downloading all the data. Again, that blows my mind. That New Horizons is so far out there in the solar system that the download rate is very slow. All of those pictures of Pluto and the moons and everything, those pictures were taken in a few days, and it took about 1.5 years to download them all back to Earth. Once that was finally done in early 2017, they were like, okay, we've gotten all the data. Let's put the probe into low power mode. They basically put it to sleep to save on electricity. And then it turns out that they found a second KBO along New Horizons' path. And so on New Year's Day, 2019, they woke it back up. I mean, they woke it back up a few days early to make sure everything was working. So in December of 2018, they woke it up to run tests and make sure that all of the equipment was still working, because they knew that on January 1, 2019, they were going to fly by a second KBO, and so they were going to get twice the bang for their buck, right? You launch this probe and you spend years traveling out there, and you're getting even more return on your investment because there's a second KBO that you can fly by and study. Here's a bit of a movie of what this thing looked like as New Horizons was flying by it. Talk about a merged body, right? This KBO is really roughed up, except that this clearly used to be two KBOs that very slowly got closer and closer. Their gravity brought them closer and closer and closer. And then when they collided, it was a very gentle merger. They just made contact. They just touched each other, and they're stuck now. One of the other weird things, here's a 3D rendering of what the whole thing looks like. From all sides. Now, here's the side they got good pictures of, but here's a bit of a movie of what it looks like in 3D. The weird thing is that it's surprisingly flat. Look at that. Right? It's not two spheres that attach themselves to each other. They're two discs that when Arikoth is the name for this thing. When Arikoth was 2 KBOs, they were two disc-shaped ones that then they attach themselves to each other, and now it is surprisingly flat. When the very first images came out, people looked at that and thought, oh, two spheres that are now merged. And it turns out it's like two frisbees, two discs that merge together to make 1 KBO. That's a bit of a surprise. That is a bit of a surprise. I did that. Okay. As of now, they put New Horizons back in low power mode. It's back asleep to save on power, and we'll see if they can find it again. If they find that there's something interesting in New Horizons' path, they'll wake it back up again, test to make sure everything is still working, and then take some more measurements. But as of now, the story of New Horizons is not done, but it is it is to be continued, shall we say. All right, let's look at even smaller stuff. Let's look at the asteroids. Comets. I forgot what order I wrote this thing. Let's look at the comets. If you think about a comet, you probably think that it looks like this, right? These big show-offs. But in fact, the solid part of the comet is tiny, right? What is a comet made of? It's mostly ice, right? A comet is mostly ice with a little bit of dust and, rock mixed in there. The comets are kind of like dirty snowballs. When a comet comes in close to the sun, the sunlight warms it up, the ice starts to evaporate, and then there's a better picture, right? The solid part, the frozen icy part of the comet is it's buried inside of the head there. Right? A comet only looks like this when it comes near the sun. And, when it comes near the Earth, because if it's near the Earth, then it's near the sun. That ice evaporates. The ice evaporates and it blows away from the comet, and that's when the comet sort of gets that head and that big spectacular tail like that. Right? The nucleus, like I said, the nucleus is the solid part. The head of the comet, where the gas starts to evaporate, is what's called the coma. And then as the gas streams away from the comet, it blows out that big tail. So the proportions here are wild, right? The nucleus is only a few dozen kilometers, between 1 and 100 kilometers in diameters, your typical nucleus, right? The solid part. But then when that ice warms up near the sun, all that gas evaporates, right? Here's what it looks like when a comet gets near the sun, right? The sunlight hits it, that gas starts to evaporate off of the ice, or the ice turns into vapor, I should say. And all that new gas expands out and forms the coma, the head. And then the dust and the gas stream away from the comet to form the tail. Sometimes, and not always, it kind of depends on the angle of the sun, the comet, and the Earth. Sometimes you'll get two tails because the dust, right? Those dust grains are falling behind the comet like a trail of breadcrumbs, right? And so the light that you're seeing there from the dust tail, right, the white light there, that's reflected sunlight. The gas, though, that gas gets heated up by the sunlight, it gets ionized, and it glows with its own emission. So this is blue, right? These comet tails can be blue because this blue light is emission spectra from the ionized, superheated carbon and oxygen, and sometimes the hydrogen, of the gas. So you're getting two different spectra here, right? You're getting reflected sunlight bouncing off the dust, and then the emission spectra of the gas. That used to be the ice, right, coming from the gas tail, or it's probably called the plasma tail because it's a gas, but it's superheated, so it's a plasma. There's a better picture. Right, so here's a close-up picture of comet Hartley. Right, here's the nucleus. Right, this chunk of ice is 2 kilometers long. Right? But then when a comet is far away from the sun, this is all it looks like, right? When a comet is orbiting far from the sun, where it's cold and it's dark, the only part of the comet that there is the nucleus. It's the solid part. But when it orbits close to the sun, then it gets hit by more sunlight, the gas vaporizes, it ionizes, and then it blows out into the coma and the tails. Comets are really small and they're really low mass, which means it's really easy to throw a comet. It's easy for a comet to get grabbed by a planet's gravity, say, especially a planet like Jupiter or Saturn, grabs onto a comet and throws that comet into a really elongated, really eccentric elliptical orbit, where a comet spends most of its time way out here, far from the sun, where it's cold and it's dark, and the only part of the comet is the nucleus. And then as the comet periodically orbits close to the sun, it gets warmer and warmer and warmer, and then the ice ionizes and it blows out that tail. There are two major regions of the solar system where you find comets. The one is the Kuiper Belt, like we talked about, right? Right, that belt of comets and Kuiper Belt objects right beyond the orbit of Neptune. And then, so that's, now we're very zoomed out, right? Here's the orbit of Neptune. Here's the Kuiper Belt. If we zoom out even more, there is a spherical swarm of comets that are orbiting around the sun at extreme distances. Right? Now we've really zoomed out where here's the Kuiper Belt, and the Kuiper Belt fits in that little blue box right there. The very last layer of the solar system, the outermost region of the solar system, is what's called the Oort cloud. And it is this swarm of comets going in all directions. Some of them are going counterclockwise, some of them are going clockwise, some are going north, some are going south. These comets are flying around in all directions, getting really, really, really far from the sun before the sun's gravity finally slows them down and they fall back in. These comets have extremely eccentric orbits. And they're not all in the plane of the solar system, right? Almost everything else in the solar system is in the same ecliptic plane, right? But the Oort cloud, some of these comets are in the plane of the solar system. Some of them go really far north or south. Their orbits can be extremely inclined, far north or south of the ecliptic. Why? Again, that's probably from the gravity of Jupiter and Saturn, right? So at some point early on in the solar system, these little comets were orbiting around the sun, and then they passed by Jupiter. Jupiter's gravity grabbed them and threw that comet in a random direction, and it threw that comet so fast that the comet's inertia took it really, 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 really far from the sun before the sun's gravity finally slowed it down and brought it back in. How big is the Oort cloud? It's hard to say, because comets are really small, and when they get really far out here, they're basically impossible to find. So we know what the shape of the Oort cloud is from the comets that come into the inner solar system, so that they're there for us to, so they're there up close for us to study. Some of these comets that we do find, their orbits will take them a light year away. The Oort cloud is a swarm of comets, and some of these comets will get a light year away from the sun before they fall back in. When you've got a semi-major axis that long, how long does it take to orbit the sun? Millions of years. Some of these comets that have been chucked really far out of the solar system now take millions of years to orbit the sun just once. Right? That's why I say this is the outermost layer of the solar system. These things are, they're still orbiting the sun. They're still bound by the sun's gravity. It's just bound really weakly for most of the time. Something really interesting was discovered in 2017. So in 2017, there we are on Earth, and we're watching this comet come into the sun, and we think, oh, okay, that's another Oort cloud comet, right? It orbits really far north of the solar system, and, you know, like some Oort clouds do, right? It comes in from the north and then comes around the sun periodically, happens fairly regularly. And so, since we just discovered this comet, let's study it, right? Look at how that comet moves, and we can trace out the shape of its orbit. What's the shape of its ellipse? What is the semi-major axis? And when they measured the shape of this comet's orbit, it doesn't orbit the sun. That comet is not in a closed elliptical orbit around the sun. That comet, which we've since called Oumuamua, it's from interplanetary space. This comet was from another star system. It got thrown out of that star system, who knows when. It's been coasting through interplanetary space for who knows how long. It got drawn in by the sun's gravity, it whipped around the sun, and now it's on its way out. This is the first time we ever discovered one of these. You know it's not from our solar system because it doesn't have a closed orbit. It's not orbiting around the sun. It came from another star. It whipped by the Earth, it whipped by the sun, and now it's on its way out, never to return again. Since then, we actually discovered a second one. There was a second comet called Borisov that was found in 2019. So we've discovered a couple of these. What do they tell us? Well, they tell us, well, the way that we study meteorites and we study comets in our solar system to tell us about the history of our solar system, these comets could tell us about the star they come from. They could tell us about what is that star like. Now, which star did this comet come from? Probably impossible to know, because we have no idea how long it was traveling through open space. But these interplanetary comets, now that we know what to look for, hopefully we find more. Hopefully it's not a complete fluke, but first time. It's the first time we ever found one of these. as I said a second ago, right? Why are we interested? Why are we so interested in these comets? Well, because the stuff that the comet is made of froze together at the very beginning of the solar system, right? Just like we study meteorites to tell us about the history of rocks in our solar system, we study comets to tell us about the history of what they're made of. Water, ices, salts, rocks. There's been a big question for a long time about where did the water come from on Earth, right? We know that water vapor can erupt out of volcanoes, so did all the oceans here on Earth, was all that water trapped in rock and it blew out of volcanoes? Or was the water delivered to Earth by comets? Did enough comets crash into Earth and deliver the water? Which is it? And there's been a lot of evidence to say it could be comets, but maybe all the water on Earth came from a lot of comets crashing into Earth. The water melted and it formed the oceans. Or maybe it was all frozen in rock. I should say frozen. It was trapped in rock, and then when the rock melted, right, when the Earth accreted and all those rocks smashed into each other, and the Earth heated up and became molten and volcanically active and convecting, and then the water vapor blew out of volcanoes. Which is it? Where did the water on Earth come from? It's probably both. I mean, the honest answer is it's probably both, and there's been a lot of evidence in the last few years that say it actually probably is about 50-50. It's probably about half the water came from comets and half of it came from rocks and vented out of volcanoes. But we know that from studying the leftover building materials that our planet was made of, which is to say, comets and asteroids. Speaking of which, let's talk about asteroids, right? Asteroids, the very first asteroids were only discovered in 1802 because these things are small, right? Sirius is the largest asteroid. It's that much smaller than the moon. Sirius is the only asteroid massive enough that it has a spherical shape. Right, in order for a planet or a moon or any body to have a spherical shape, it needs to have enough mass, it needs to have enough gravity that its gravity will pull all the rocks and ice together, pull it toward the center so that it takes on a rounded spherical shape. Sirius is the only one that meets that threshold. All of the other comets are lumpy and irregular because their gravity isn't strong enough to pull it into a spherical shape. These things are so small you can't see them with the naked eye. You can't see an asteroid with the naked eye. You need telescopes to see them, and by 1801, 1802, the telescopes were getting good enough that you could find these things. What do they look like in a telescope? Well, they look like faint little stars, right? This is why we call them asteroids, because asteroid, the word aster is from the Latin for star, so asteroid literally means a star-like thing. Because these rocks are so, I mean, they're mountains, right? The asteroids can be dozens to a few hundred kilometers in diameter, so they're mountains basically. But when they're a mountain that is several astronomical units away, they just look like little specks in your telescope. They look like little specks in your image. They look like faint little stars. The reason that you know you're looking at an asteroid and not a star is that asteroids move around the solar system, and so you can see the asteroids move relative to the background stars on the celestial sphere. Most of the asteroids, and I got a map here in a second, but most of the asteroids in our solar system are in the asteroid belt, which is in between the orbits of Mars and Jupiter. So here's Mars, here's Jupiter, right? Here's the main asteroid belt, right? What is the asteroid belt? The asteroid belt is this, it's this swarm, it's this belt of most of the asteroids orbiting between Mars and Jupiter. But not all asteroids are in the asteroid belt. There are several other families of asteroids. So The Trojan family are the ones that are coded in green. There are other families called things like the Autons, the Apollos, the Amors. We name the asteroid families by common orbital shapes. So the red ones are the ones that cross the orbit of Mars. The blue ones cross the orbit of Earth. So there are some asteroids that orbit closer to the sun than the asteroid belt, and there are these big ones that orbit out at the orbit of Jupiter. This map is a little misleading, right? You'd think with a map like this, the asteroid belt must be absolutely jam-packed with asteroids, right? Well, not really. Because the dots to plot out, the dots that are plotting out where the asteroids are way too big, right? This whole area here goes from between 2 to 4 astronomical units. So it's two astronomical units wide. Yes, there are hundreds of thousands of asteroids in the asteroid belt, but each asteroid is really small compared to the distance between them. Right? The asteroid belt is mostly empty space. If you added up all of the asteroids, and yes, there are 500,000 asteroids in our solar system, but if you took all 500,000 asteroids and added them all together, they would only add up to be about 4% the mass of the moon, which is not a lot of material. Right? I said before, right? The asteroids are what? They're the leftover building materials of the solar system. They are big rocks. They're big rocks that are left over from the formation of the solar system. Why didn't they ever accrete? Right? Why didn't all of these rocks ever crash into each other and form a planet? And the answer is because they're not allowed to. And there's a reason why the asteroid belt is orbiting right inside Jupiter, and that's because Jupiter's gravity keeps the asteroid belt stirred up. Jupiter's gravity is strong enough to keep whipping up the asteroid belt, keep the asteroids moving, so that they can't get too close to each other. They can't get close enough to crash and merge and accrete and form one big planet. If there was more material in the asteroid belt, if there was more mass with stronger gravity, maybe they could have. But it's not enough material, right? The asteroid belt is just a loose belt of little rocks. I mean, little rocks meaning, the size of mountains. And their mutual gravity is not strong enough to cause them to accrete. So there they are, just a bunch of rocks orbiting around the sun, constantly being agitated and stirred up and spread out and kept loose by the constant gravity of Jupiter. So it's not like, the asteroids are like flying mountains. They're mostly rock with a little bit of ice, right? I said a second ago, comets are mostly ice with a little bit of rock. The asteroids are mostly rock with a little bit of ice, right? But it's not like Star Wars, right? Our asteroid belt is not a belt with lots and lots and lots of rocks. It's like traveling through the asteroid belt is actually not this hard, right? It's not like if you want to get through the asteroid belt, you've got to dodge and weave and avoid all the rocks. Our asteroid belt, this movie was not set in our solar system, so this is a different asteroid belt, but it's not ours, right? This is not what our asteroid belt is like, right? The distance in between the asteroids in our asteroid belt, the distance between the asteroids is much greater than the size of the asteroid belt itself, right? Our asteroid belt is mostly empty space. If you wanted to get out into the outer solar system, if you wanted to send a probe, if you wanted to fire off New Horizons or Juno or Cassini, right? If you wanted to send a probe into the outer solar system, you could just fire that probe into the asteroid belt because the odds of you hitting anything are basically zero. It's mostly empty space, right? If you do want to go near an asteroid, you got to aim for it, right? You've got to send a probe with a camera up to an asteroid, and you've got to intentionally aim for it. In order to get close enough to take good images, you can't just blindly travel in any direction and hope to get close to an asteroid, because the odds of you getting close to one are pretty darn low. Which means in order that we know what asteroids look like up close because we've sent missions. And taken these close-up pictures, right? Here's a picture of asteroid Eros, right? Lumpy and irregular because the gravity is so weak, right? The gravity can't pull all that rock together into a smaller, tighter, more spherical package. The rocks are allowed to just lump out in all directions. And this thing's not that big, right? This asteroid is a few dozen miles long. And notice, rough, old, heavily cratered. Even the small bodies in the solar system are covered in a multitude of even smaller craters, made by even smaller objects, right? We've said it before and we'll say it again, right? The smaller something is in our solar system, the more of them there are, and that's true even at small scales. When you look at the small things in our solar system, they've been hit by a larger and larger number of even smaller and smaller things. Some of these asteroids are a little smoother. I mean, still heavily cratered, but a little smoother. Some of them are rough and rubbly. They've been hit more recently. This asteroid, Itokawa, has been hit more recently, and whatever impacted on it sent a whole bunch of rubble and debris out off the surface, and then this asteroid's gravity slowly brought all the debris back to lay there on the surface. Right? The gravity around these asteroids is so weak that it's really easy to throw the debris really far, and then slowly but steadily the gravity pulls the debris back in. A lot of the most recent images of asteroids were taken by the Dawn mission. The Hayabusa mission to go to asteroid Itokawa was done by the Japanese space agency called JAXA. And when NASA decided that it was going to send a probe to some asteroids also, NASA and JAXA, the Japanese space agency, worked together to help each other out and share data and share results and share expertise. And so NASA decided to visit two of the largest asteroids, Vesta and Ceres. Here's what Vesta looks like up close. Rough, heavily cratered, old, right? Hit by a large number of lots and lots of smaller things over the eons, over the billions of years. Here's what Ceres looks like, right? The Dawn went into orbit around Vesta for several years, and then once they had studied everything about Vesta that they wanted to know, they left Vesta and they went into orbit around Ceres. And when they got up to Ceres, remember Ceres is the largest asteroid in the asteroid belt. Ceres is the one that is the only one that has a spherical shape. And everybody got really excited when they took this picture of this crater on Ceres, because like, you know, hey, oh, there's a crater on this asteroid that has a shiny white stuff at the bottom of a crater. And everybody starts going, oh, I know what that is. I've heard this story before. I heard this story on the moon. I heard this story on Mercury. That must be ice. There must be ice frozen into that crater. And then you get close, and actually it's salts. That at the bottom of this crater, there are these salt deposits. Now, how do you get salt to the surface of a world? Well, probably with water. That trapped in some of that rock was really salty water. Like there was water with some salts and minerals and stuff dissolved in it. And then each of these little white splotches is it's where the water seeped to the surface, or maybe it erupted onto the surface. Right? Those white patches are essentially places where there was a little heat left way back when. Yeah, Ceres, I mean, you can tell from the photos, right? Ceres is rough, old, geologically dead now. But back when Ceres had a little bit of heat left, it probably melted that water, and the water bubbled its way up to the surface, or it erupted onto the surface in some kind of geyser. And when the water hit the surface, it took the salt with it. And so each of those white spots for a while was like a pool of salty water that erupted out of a geyser. And then the water got hit by sunlight, and the sunlight evaporated the water. And when the water was gone, all you're left with is the patch of salt behind. Those salts are a lot of things like sodium and carbonates, um, a bit like baking powder. Um, Powdery, white, salty compounds. Um, Not unlike salts that you'd find in the oceans, right? There's sodium in the oceans, there's carbonates in the oceans. Um, Not the ice that we thought we had found, but unique and interesting in its own right. Evidence, right? Evidence that there was some geothermal heat driving the geysers when, back when there was some heat left over, before Ceres went totally geologically dead. The smallest objects in the solar system are going to be the meteoroids, because once you've talked about the Kuiper Belt objects and the asteroids and the comets, now you're just left with the huge multitude of tiny little things, tiny little rocks and chunks of ice that are still orbiting the sun, right? And our solar system is replete with little micrometeorites and well, not meteorites yet, but little rocks zipping around, orbiting around the sun, and occasionally crashing into the moon or the Earth. Um, we've talked about the Allende meteorite before, right? It crashed into Mexico in 1969, and this is one of those primitive uh, meteorites that is left over from the beginning of the solar system. I clarified myself a second ago because we have a little bit of vocabulary here, right? If you have a rock, if it's just out there in space orbiting the sun, it's called a meteoroid. So, while it's still out in space, it's a meteoroid. If it gets too close to the Earth and it gets grabbed by Earth's gravity and starts falling through the atmosphere, then it's a meteor. Right? A meteor is the rock that, while it's falling through the atmosphere, once it hits the ground, now it's no longer a meteor, now it is a meteorite, because ite, ITE is geology speak for a rock, right? Right? Granite, quartzite, right? Rocks for us to dig up and study. So if it's a meteorite, that means it's hit the ground, now we can dig it up and touch it, right? And analyze it. Right? A meteor, it's not a shooting star, right? A meteor is just a little rock that is falling through the Earth's atmosphere, and I say falling, hurtling through the Earth's atmosphere, right? Earth, as these rocks fall to Earth, they get moving faster and faster and faster and faster and faster, and then they're plowing through the Earth's atmosphere, and Earth's atmospheric friction is warming up the rock, and when the rock warms up, it starts glowing with its own blackbody spectrum. right? When you see a meteor in the sky, what you're seeing is the glow of a rock as it's burning its way through the Earth's atmosphere. Most of the meteors never reach the ground, right? Most meteors burn up and they disintegrate as they're falling through the atmosphere. It's only the really big meteors that can burn all their outer layers away and still leave part of the rock behind to actually hit the ground. And, most of the Earth is ocean, right? But most of the Earth is uninhabited. So most of the time, if a meteorite hits the ground, it crashes into the ocean or it crashes somewhere where nobody lives. But every once in a while, a meteorite, pardon me, get my vocabulary straight. Sometimes a meteorite will hit the ground close to where people are, which is great, because that's exactly what you want. Because why are we studying these things? Right? We study these things because they're left over from the beginning of the solar system. There are ancestors, yeah, kind of. These are the rocks and water, that if there's any water molecules trapped in the rocks, if there's anything trapped in the rocks, this is the kind of stuff that Earth formed out of. Some of these meteorites are, iron and nickel, just metals, and some of them are a more interesting combination of different compounds, like the Allende meteorite is. But when a meteorite hits the ground, there's a rush to go and catch it. Not catch it like it's you're not catching it in midair, but catch it before it's been sitting around too long. Because as soon as that meteorite hits the ground, it's going to start getting contaminated, right? You want a pristine sample. If you're going to do things like count up the daughter and parent particles in order to get the radiometric dating, or if you're going to study the chemicals that are in that rock, if you're going to study what's the elements and the molecules, if you're going to study what this meteorite is made of, in order to know what the solar system was made of billions of years ago, you want to get that sample, you want to get that rock before it starts getting contaminated by Earth stuff. Right? As soon as it hits the ground, it's going to get dirt on it, or rained on, or bugs crawl around on it, and plants start growing on it, right? The longer it's around, the more contaminants from Earth there are, and that can make it really tricky. Right? So if you know that there's a meteor coming toward the Earth, and now we have the technology to do that, then you can catch it right after it lands. The first time this was done really successfully was in 2008, because there's an amateur astronomer in Tucson named Richard Kowalski, and he's got a telescope in his backyard, and one thing he does is track asteroids and looking for meteors and all that kind of stuff, and he actually discovered a meteoroid as it was on its way to Earth. He actually discovered it 2 days before it crashed into the Earth. And so they were able to predict, well, if it's heading straight for us, it's going to crash into us in 2 days. Where's it going to crash? And based on the path of the meteoroid, they predicted that it was going to crash into Sudan. So he contacts some of the meteorite people at University of Arizona, and Peter Jeniskin is the head of that project. He gets his team together and travels to Sudan, and they go out into the desert of Sudan, and they find, when these rocks hit the ground, they shatter into a million pieces. So there's debris all over the desert, right? They find fragments of the original meteoroid. Now they are meteorite fragments scattered all over. It had only been there for a couple of months. And this is the Sudanese desert, so that it's not a lot of rain to worry about. But still, you want to make sure that you get it so that you can study it as soon as possible. This happened just recently. In February of 2021, a team tracked a meteoroid just as it was about to hit the Earth. So they tracked it. They have cameras that saw the flash of the meteor as it was falling through the atmosphere, and they were able to predict where it would land. And they said it would land in this town in England, Winchcombe, I assume it's pronounced. Unfortunately, it was 2021, and everybody was under lockdown. So the team that wanted to get out there in England and find this meteorite couldn't travel. And so they put the word out over the internet and said, hey, anybody that lives in this area, if you want to go out and look in your backyard and look around, see if there's any rocks that just hit your driveway, we'd really appreciate it. And they found a bunch of fragments. People in this town went out and started finding all of these fragments of this meteorite that had landed, literally some had landed in the street and they saw a dent in the asphalt of the road. Some of these fragments landed in people's backyards. What did they find? What do you find when you do this? Well, in these meteorite samples, they found water. They found water that has a lot of the similarity. I mean, water is water, but it looks a lot like the water on Earth, which seems like a silly thing to say, but water on Earth has certain ratios. There's certain ratios of different isotopes, right? Water is made of hydrogen and oxygen can have different isotopes. So not every molecule of water is exactly identical. And water on Earth has a certain ratios of different kinds of isotopes and stuff. And the water that they found inside these rocks was very similar. Which again, goes back to that question I was saying, where did the water on Earth come from? Did it just come from comets, or could it have come from rocks bringing water with them? And the evidence from not just this one meteorite, but lots of meteorites that they've found samples of is it could have come from the asteroids too. Like I said, it looks like it's about 50-50. That the water here on Earth might have come from, water molecules that were trapped in rock until they crashed into the Earth, the rocks melted, the water was released, and it turned into steam and vented out of volcanoes 4 billion years ago. Some of the other things that you find in these old meteorites are things like amino acids. Right? What are amino acids? Amino acids are the building blocks of life. They're the kinds of things that proteins are made out of. Some of these meteorites, you find amino acids frozen in the rock. And that's really interesting. Because again, if you're studying a meteorite that's been sitting there on Earth for a long, long time, of course you're going to find water on it. It's been rained on for years. Of course you're going to find amino acids because grass has been growing on it, or moss has been growing on it, or, bugs crawl on it, right? It's like, oh yeah, of course there's amino acids. They're from Earth. You want to catch these meteorites right when they land, so there's been no time for rain to add water to it. That way all the water is from the rock itself. You want to make sure that there's been no time for Earth life to get inside all the nooks and crannies and contaminate the sample, because you don't want to cut into this rock and go, oh my gosh, I found grass in this asteroid. Grass comes from outer space. Oh no, it's just Earth grass that grew on there years ago, right? When you find these rocks that just landed, and when they've got inside the rock, when they've got water and when they've got amino acids, that means the water and the amino acids actually comes from outer space. It actually was trapped in the rock at the beginning of the solar system. And that means that when those asteroids when those meteorites and asteroids crashed into Earth over and over and over again during the period of heavy bombardment, they didn't just deliver rock and metal to Earth, they also delivered their water, their amino acids, the building blocks of life. There's still a big question about how did life happen on Earth? And how does life happen in the universe, right? Did life on Earth have to start from scratch? Or did it get a bit of a head start, right? Maybe life on Earth didn't have to start from the absolute bare bones building blocks. Maybe life on Earth got a little bit of a head start from things like amino acids being delivered by these protoplanets, planetesimals, meteorites. Right? Back at the beginning of the solar system, when the Earth was still hot and the oceans were just forming, in that water, in the water of the early oceans, there might have been some amino acids delivered from the meteorites. And other organic chemistry, right? Other kinds of molecules that you might study in organic chemistry, not just amino acids, but ethanols, formaldehydes, alcohols, salts, that kind of stuff, right? The kinds of things that life needs to survive. They may not have had to evolve from inorganic chemistry. That life on Earth may have been given a bit of a boost, a bit of a head start. And that head start allowed those amino acids to get together, form proteins. Proteins eventually got together to form cells. The cells started dividing and multiplying, and eventually life took off on Earth. If that's true, if it's true that life on Earth got a head start, why not other planets? Right? If every planet has to evolve life from scratch, that's hard to do. And if that's really hard to do, that might mean that life in the universe is rare. But if every planet gets hit with these rocks, and they did, and if that happens in every exoplanet system, then maybe that means, right, if life on a planet can get a head start, right, if things like amino acids can start forming even before the planet forms, then that might mean life gets a head start on a lot more planets than just ours. And that might mean that life in the universe, life on other exoplanets, might be easier than we thought. And if it's easier, that might mean life in the universe might be more common than we think. All of that, these big implications for where are the aliens? Where should we be finding life in the universe? Is there life in the universe? Where are all the other aliens for us to talk to? Are they there at all, or are we alone? Those big answers to big cosmic questions coming from these little rocks crashing down on us from the sky and occasionally doing property damage. They look like, grayish black rocks. I mean, it's cool. You found a space rock. I mean, that is pretty cool. A space rock lands in your backyard. But when you study these things, sometimes these rocks, sometimes these meteorites have molecules you don't expect that tell you something big about why we're here. Why are we all here on Earth and not somewhere else? Why are we not on Venus or Mars? And if we're here, are there living things on other planets? And the more we look, right, the more we look for water in the solar system, we find more of it. When we look for amino acids, we're finding it. Not everywhere, but a lot more places than we expected. And when we look for things like water and amino acids out there in the galaxy, in other systems, other places, around other stars and other planets, we're finding some of it there too. this is still cutting edge stuff. We're still getting the knowledge and the technology to look for things like water and amino acids and methane and oxygen around other stars. But if we're finding it all over the place in our solar system, that means finding some of it around other stars is looking a lot more likely. That's why we study these minor bodies, because they tell us about how we got here, why are we here, and also, could there be other us's? Could there be other living things, either things as basic as bacteria or as complicated as intelligent life, among all the other exoplanets we're finding? Now that we can find the exoplanets, and we're finding thousands of them, now we go for the next step. Now we say, all right, where's the life? And these little rocks give us a key to unlock the next door. All right. Thanks, everybody. If you've got questions, go ahead and email those to me or come into office hours, and we'll take the next lesson from there. Have a good one, everybody.